Okay, hi everyone. Thanks for attending my talk. Good morning. This is a collaborative work just to start, and lots of people involved from Oak Ridge, Lawrence Livermore, and Sandia. And so the topic is machine learning approaches to ensure statistical reproducibility. By machine learning, I mean multivariate approaches, testing approaches that have been appearing in these machine learning journals. And by statistical reproducibility, I just mean climate statistics. So let me get on with it. So the motivation for the talk comes from this NGD software algorithms project that Andy Salinger is leading. The goal of the project is to effectively use DOE's leadership class HPC machines, and part of it is to improve model trustworthiness, and that's where we come in. We were trying to do these non-bit tests. So if you look at code evolution within E3SM or any other large code, there are changes that would be bit for bit reproducing. For example, when you add a new output variable, or you want to add a new comp set, or a minor bug fix, for example. But then there are also these non-bit for bit changes, some for which you want the climate to change because you're adding new parameterizations or you're improving your tunings. But then there are cases where you just want to change something to improve the efficiency of the code, for example, by refactoring or putting it on a GPU kernel, maybe porting it to a new machine, where you don't want the climate to change and you don't expect it to change, but there might be issues or bugs from different things that might come in that might change the climate statistics. So our goal here is to have a test for the null hypothesis that the climate simulation, when you change something unexpected, that you change something that's causing an unexpected bit for bit change, there is no actual change in the climate statistics. So to continuing on the motivation, we know that with computers, it's all truncated floating point arithmetic. So 10 to the power minus 14, 15, that's the with double precision, right? And also we know that the computers can be non-associative if you're adding very large numbers, and it might result in round-up differences that might change the last digit, for example, the last couple of digits of the number in this truncated floating point environment, and this might happen because of optimizations or porting your code to a hybrid architecture where the order of computation changes to improve that efficiency. And climate models, as we know, are basically chaotic nonlinear systems, and any small change, as we know from the Lorentz attractor, would lead to a new state in a very short time period, and so the round-up differences grow quickly. And so again, the problem is if we introduce some change that is causing a non-bit for bit solution reproducibility in the model, how do we identify systematic bugs that might have been introduced, as opposed to these inoculate round-up differences that grow as well, right? And so within E3SM, there are these testing suites that are run nightly for bit tests. So they're just comparing the numbers to see that they're exactly the same. But then this past year, we have added these non-bit for bit changes. So there are tests that is the convergence test that's Huiwan had developed that. And there's this perturbation growth test that Balwinder Singh had developed. And then we have this climate reproducibility test that I worked on. And so the first two tests, the convergence and the perturbation growth tests, are for the first few time steps, and they look at the growth in errors or the convergence of the model in the short time frame. But we are looking at the climate reproducibility in the sense that we are looking at climate statistics as can be captured within the first year for the atmosphere model, and within the second year with the atmosphere post-ocean model, as we'll see later in the talk. And so this improves on the expert opinion and ad hoc tests that have been in place for these non-bit for bit changes that have been there, right? So let me go into the approach that we have been using. So we use a short simulation ensemble approach where we have a control run, and we perturb the initial condition of the control run, and we run several ensembles. So what you see here is a plot of the growth of the round-off differences that were introduced at the initial condition. And you can see that within 21 days, this is for the atmosphere, ocean, prescribed SST, FAMA kind of runs. And you can see that within 3 or 4 weeks, the model, the error from the round-off differences has rated or so. And then the models, the ensembles themselves are independent of each other. So there are 150 ensembles in here, each just differing in the initial condition. And that's just the temperature, the initial 3D temperature has been perturbed by a uniform distribution of 10 to the power of minus 14, right? So We just pick numbers and we perturb the initial condition for each grid point for the temperature, and we can see the differences that we get from that. So our problem is, if we introduce a change in the model, and then the errors would grow in that too, but then we want to differentiate that change from the roundup differences that might happen. So this cartoon is just showing that we want to see if the two ensembles that we run for the perturbed case, where you have changed something, versus the control case where you believe that the model is correct, and you want to compare these two, the spread in the model, and see if they're statistically similar. So if they're on top of each other more or less, then we say that okay, they're similar. But if they're different like this, there's an abstraction that oh yeah, the model is different and something went wrong when we were doing a port or adding a kernel in the model. So the climate model itself is a high dimensional problem, and we typically have very low ensemble sizes, so the sample size is very low basically. So this is a problem which is a multivariate problem for high dimensions and low sample sizes. So again, to properly state my approach, we are comparing two ensembles, a control ensemble versus a short ensemble, and we use we ran the model for 13 months in this case, and we throw away the first part because the errors are still, the roundup differences still grow for the first 3 or 4 weeks. And then we hope that this short approach would quantify the natural variability as much as we can for the 1 year short-term period. And using ensembles can also be computationally efficient, as we'll talk in the next slide. But given this approach, we have these, for these high dimension, low sample size problems, we have these 2 sample equality of distribution tests from the machine learning community that we can also use. So examples are cross-match test, energy test, kernel test, which we'll talk about later. And these are some powerful tests which are distribution free. So the underlying distribution of the variables doesn't matter there. And they can be effective at high dimensions, low sample sizes. They've been used in other fields. So just to talk about, just to digress a little bit about simulation ensembles. So I want to tell you that, or show you that short ensembles or ensembles are more efficient than a long run. For example, say you want to do a 100-year run versus 100 ensembles for 1 year. If you run a long run, then if you want to increase your throughput, so you want to increase your number of nodes, for example, right? And then in that case, what you're doing is you're spreading your work throughout the machine, and each node gets less and less work, and only increasing the MPI communications. So it gives you the throughput you need, but then you're not using your machine efficiently. But if instead you pack all of these 100 ensemble members together on the same amount of nodes, you're immediately increasing your workload on each node by 100. So that improves your parallel scaling for the model. And if you can pack a large number of jobs like that into larger node counts to improve your efficiency, to improve your efficiency, then you can get higher priority on leadership class machines, right? And so an example here is we ran this on Titan a few months or years ago, where we had a long run. This is for the NE16 model, which has 1536 elements. We use 96 nodes, and each node would get 16 elements for computation. But if you pack these short ensembles together, we use 48 nodes for each run. So we pack double the work instead of like 100 times the work. But in this case, we were able to use 4,800 nodes together, and so we could use the cube references on Titan. So these short and simulation ensembles could be used for solution reproducibility tests, as we'll see quickly later, and then they can also be used for scientific applications. And one such application we had done in the past was using this approach to understand the effect of sulfates on the upper ocean. So what you have here in the gray line and the cartoon here is the control case. We ran the model for a long time with 1850 sulfates, and to understand the effects of 2000 sulfates, what we did was we perturbed the initial conditions for each of these years. Not the initial conditions, we just perturbed the sulfate aerosols in the model for each of these years, and so we can pack these together into one ensemble, and then we could run it as one job, and then very quickly, and then we could get results like whatever we want to look at. So this is a plot of the SST and precipitation of the difference between this ensemble versus this long control run. So in a sense, we are comparing apples to apples, because the initial conditions for the control run and the perturbed ensemble are very similar. It's just the difference is only in the sulfates, right? And we don't have to run a long case with the sulfates to understand the upper ocean dynamics. So, sorry, coming back to the tests here. So let me talk about the test that we have been using. One of them is the energy test, and let me describe it very quickly. So the energy test, it depends on this metric. So in this case, we are using 150 variables from the EAM output. So 150 prognostic variables from the EAM, and so we have this 150 dimension space. And what this test does is computes the distances between these multivariate data points within the ensemble and across ensemble. So if you have a perturbed ensemble and you have a control ensemble, you compare these distances. So if the distance across the ensemble if the average distance across the ensemble is much greater than the average distance within ensembles, then you say that, oh, okay, the models differ and these climate statistics differ. So basically, small values say that they belong to the same population. Small value of this metric E that we have here, and the null distribution of this metric E, or what you should expect from a population where from a sample where the population is the same, is derived by resampling. Similarly, we used another test called the kernel test. Here, instead of these Euclidean distances, there's this pairwise kernel function that I use. So these could be like Gaussian kernel functions, or these could be the Blachian kernel functions. And then the way this works is you maximize this kernel function for one ensemble and minimize it for the other ensemble, and then you fit these pairwise functions to each of the data point pairs. And then you compute this metric. It's called the maximum mean discrepancy metric, or the MMD. And then you look at that its distribution using resampling again and again. If you have small values of MMD, that means the samples are coming from the same population. If the values are larger, then probably they're coming from a different population or a different climate state. The other test we incorporated was this KS test, or the Kolmogorov-Smirnov test, which is a univariate-based test. So if you have 150 variables, we run this test on each of the variables separately, and then we can look at all the 158 variables, and a test statistic in this case, or the metric for the larger null hypothesis that the climate is same or different, is the number of variables that fail this test. And if you have like 100 variables, you would expect 5 of them to fail if you're doing a 95% test, just by chance, because that's how the design of the test works. And then there'll be correlation, so that might change it. So again, you can derive the null distribution of this test statistic using resampling. So let me just talk about resampling quickly. So what we do is one approach is this perturbation testing approach, or perturbation approach, permutation approach, where you pull in both the ensembles, the control and the perturbed ensemble, into one big pool, and from that you draw these samples back again, but randomly, and then you compute your test statistics. For example, the energy statistic, you'll compute it again for each such resampling, and when you do it a number of times, you can get approximate null distribution of the statistic of how it should behave if they come from the same population. And then when you go back and you can look at the original data and look at that, the metric from that, the E distance, for example, then you can compare it to this distribution that you derived from these resamplings, and you can say if it's off the charts or if it's within the distribution, and say if your test is passing or failing. So just to give an example, we have this. So we did this test case where we have this control run, and we perturb this ZMC0 ocean parameter, which is in the Zhang-McFarlane parameterization scheme, and controls the conversion of cloud droplets into precipitation. And we did these ensembles, perturbing the initial conditions for both the control case and the modified case, where we changed ZMC0 ocean from 0.007 to 0.045. This is done on the NE4 model resolution. And we can see that if you did resampling, you would find that only 13 variables should fail in an ideal case when you have 150 or so variables, if they're coming from the same population. But since we changed the ZMC0 ocean from 0.007 to 0.045, we are failing 119 variables when you do this test, the KS test, for example. And so we say that, okay, these are coming from a different population or a different climate. So this is a different climate of the model if you change that, if you do add that perturbation. But this does not quantify how much your test can catch and how many ensemble members you would need. In this case, we use 30. So for that, we have done a formal power analysis where we change the ZMC0 ocean incrementally, slowly, gradually to different numbers, and then we run these ensembles again, and we do the resampling again for each of the, and we do tests again and again from these resamplings. And so, for example, we'll pick, so we did this 100 member ensembles for each case, and then we'd pick 30 members from each of these sets, and then evaluate them for the null hypotheses. So we do 500 times, and what you see here is this power analysis curve. So on the x-axis, you see the values of ZMC0 ocean that we had used for this power analysis, and the y-axis is the power or the probability of correctly rejecting the false null hypotheses, that the models are different, because we know just by changing the ZMC0 ocean that we have changed the model. So if you look at the red line here, what you can say from this is that if you use 30 member ensembles, you can identify changes in the model almost 100% of the times if you change your ZMC0 ocean from 0.007 to 0.0075. So when we say that our test is passing, what we mean is that our control case or your perturbed case is the same as what you would expect to change from 0.070 to 0.075 for the ZMC0 ocean. So this informs the user of the test that, okay, when you say pass, it's not exactly similar, but it's similar in this statistical sense. And so if the user says, oh, this is too much, we want it to be a smaller change, then we would use a test which has a ensemble 60, where you can catch differences as small as 0.072 with like almost 90% confidence. So we have done this power analysis for energy test, kernel test, and this case testing framework that I talked about. And you can see from these plots is that with the case testing framework has the largest power because it can catch smaller differences with the same ensemble size. For example, the energy test can, with 60 ensemble members, it can only detect differences going from 0.070 to 0.0025 of the ZMC0 ocean parameter. Similarly, same thing for the kernel test. So here we say that the case testing framework has more power than the other two tests. We have done this for several other parameters too, tuning parameter changes. So this is another example for DCS, which is in the cloud microphysics scheme. And we can again see that the case testing framework has more power and can detect changes going from DCS default value of 400 to DCS's value of 390 confidently with almost 100% certainty. Right? So again, we have done this for a large number of variables as tuning parameters I have listed here on this slide. And we have consistently found that the case testing is the most powerful of all these tests. And so that's what we have implemented in the non-bit-for-bit test in E3SM testing. And a use case for this test was, we did this last year, where Edison was being retired, and the runs had not, the deck runs had been, the low resolution deck runs had been done on Edison, and the future runs were planned to be done on Cori. So we were tasked to test if the runs that you did on Edison are similar statistically on Cori, and we did this for the NE4 resolution using 100 member ensembles, and on at the NE30 resolution using 30 member ensembles, and we found that yes, our tests passed, meaning that if you did the same run on Cori, you would get a statistically similar climate. So adding confidence that we can run these new simulations on Cori instead of Edison. And we got similar results from the convergence test that we wanted worked on, and the perturbation growth test that Balwinder Singh had worked on. So we have incorporated these tests into the E3SM testing framework. All three tests, Huiwan's, Balwinder Singh's, and the case testing framework. And Joe Kennedy had worked on this, and he had put it into the C- and in the E3SM custom test part of it. And we have these were being run nightly, and we recently figured out that they have not been running properly, and we are working to fix it. And we have a new person to work on to replace Joe Kennedy. His name is Michael Kelleher, and he's right now working on it to fix the problem. And so these results of the tests are given in a summary form in the on the Dash website, but then there's a link to this broader website. We can look at the plots and the QQ plots of all the variables that we've tested and things like that. And so this E framework that Joe developed, it's a Python-based toolkit, and it runs these control and ensembles. It post-processes the data, and it conducts the test, and it publishes these results. So that was the atmosphere model that we had worked on. Let me talk about the ocean model that we have been working on recently to import these tests onto this MPAS ocean framework. And what we have here we wanted again to use a low resolution model because we wanted to be have a computationally minimum impact on the machine, on the project. And so we use this 240 kilometer resolution, the QU240 resolution of the MPAS Ocean model. And this is only typically used for testing and not for science typically. So what we did was that we ran this, we took this model out of the box and ran it for 100 years to see if it reaches a quasi-stationary state at least. And what we found that at about year 50, it's reaching this state that's stable for the next few years. So right now we branched out from here to create our ensembles. But we are running this right now for a longer term period to see if we can actually get to quasi-stationarity with this model. And then we can use those initial states to run our model. So we perturb, so at year 50, we perturb the initial conditions using the Python script to add these temperature perturbation, machine precision perturbations to the 3D temperature field of the ocean. And we are saving these perturbation conditions, and we're using create clone to generate ensembles, and then we perturb the MPAS streams ocean file to change the initial condition file to the same new files. And we're doing these 100 or 150 member ensembles with that. So in the future, instead of doing this hands-on approach where you have these Python scripts to do these things, we want to replicate the capability that we have in the EAM for doing these multi-instance and multi-instance runs, where we can also perturb the initial conditions, the pertlim capability, as to say, just by tweaking a nameless parameter, for example. And so the approach here is similar. So we are looking at the error growth, and then let the roundup differences grow, and look at the time period where we have a quasi-stationary state to look at the climate statistics. So the plot you see here is the L1 norm, or the relative difference in temperature at the sea surface temperature. And you can see that it grows from the machine precision levels all the way to order of 1 or 2, and it takes about a year to do so, and it's still growing here. So we are using this this ellipse that I show here, the year 2 of the simulation, to do our testing here. And this is again a GMPAS, a normal year forcing case, so it's not a coupled run, so just the ocean. And in the control case, we ran for a number of years, and you can see that there is still a minor trend in there, so it's not reached quasi-stationarity yet. So the hope is that when we run the control case for a longer time period, going beyond 100 years, you might get a state where the trend vanishes, and so it would be a more robust result of what we show. And then the approach here is, instead of the 150 variables that we get from the prognostic variables that we get in the atmosphere, here we only get 4 or 5, and so we want to test. And the other part of this is that the ocean climate is very spatially heterogeneous. So what we decided was to do it at each grid point instead of looking at the variable in a global average sense. So we are evaluating these variables at each grid point. So at the 240 kilometer resolution, there are about 7,000 points. During this test at 7,000 points. And so we do the KS test, as I mentioned earlier, and we also are using a new test, which is called the Cuccioni test, which has in literature has been shown to have a better power, and it's a line-based non-parametric test like the KS test. So the blue line here that you see here is we changed the GM kappa parameter here from the default value of 1800 for this resolution to 600, and you can see that as this error grows, we are getting a different climate, and the blue lines show that here. So it's clearly a different climate, and if we do a test, it should pass that. Let me just quickly talk about the Cuccioni test. It's just a rank-based test. If you have, if this is a univariate test, so if you have a variable and values of that variable, you rank them, and the Cuccioni test is the test statistic metric where you are adding the rank, when you're taking the squares of the rank and the contrary ranks meaning the sample size minus the rank minus u. So V is sample size minus u, basically. And so the Cuccioni test would tell you that if you have a larger statistic, that means that they're coming from different population, but a smaller statistic would mean that they're coming from the same population. This is popular in the other fields of hydrology and quality control, etc. So the other problem here is now we have a large number of tests that we are conducting. So the issue of multi-testing come up, where if you're doing a 95% confidence test, then 5% of them would fail. And if you have correlations, certain other number of test points would also fail. So there are these approaches where you can correct for this kind of multi-testing and correlations. And one of that approach is called the false discovery rate, And what it does is it corrects the critical value that you have. So if you have a critical value of 0.05 for a significance level of 95%, then this adjustment would reduce it substantially down so that none of the points would fail. And your global null hypothesis would be, if none of the points fail, then the null hypothesis is safe. Otherwise, you have to reject the null hypothesis. And it has been shown to be robust for correlated tests when you have spatial correlations involved, and it's used in testing field significance. So this is just to show what the FDR approach does. So if you see the dashed line here, that's the 0.2 p-value that in this case the test would reject. But if you have used the FDR approach, it will only reject points that are below this this cross point that's shown here. So that's what the test is doing. It's reducing the alpha for testing. So to test if that really happens, we did this bootstrap approach. We did a large 150 member control ensemble, and we randomly picked 30 members from it, and then we applied a KS test and Pucconi test at each grid box for the sea surface height in this case, and we repeated this a number of times. And what we find is for 95% of these resamplings for the KS test, if you apply these corrections, the FDR corrections, none of the points are failing, meaning that we know. So we know that these are coming from the same population, but the test is also catching that. And if you don't apply that correction, then we have 426 points failing out of the 7,000. So that's more than the 5%. For the Pucconi test, it's not exactly 0. If you apply the correction, it's actually 15. And so we use that value when we do our tests. And if you don't do any corrections, it's actually 643. So this is the case, as I just talked about before, where we changed GM kappa from 1800 to 600, and you can see this error growth and roundup difference growth, and then at the end the model is much different from the control case, and so our test rejects this. And again, but this does not inform you about the sample size needed or what how low the model can catch to change GMs to smaller values. So we again did a power analysis with this incremental change in the GM kappa parameter. We did these 100 member ensembles with discrete values of GM kappa. And then we did this power analysis using by drawing resamplings of different ensemble sizes. And so this is the result from that. So the first plot is from the KS testing framework. The second plot is from the Pucconi testing framework. And we see that they have about similar power if you want to more or less. And the GM kappa, you can detect differences as small as going from 1800 to going to 1799 with very high confidence. So this is work in progress, and we want to enhance this for other parameters too. So just to summarize, since my time is almost up, I guess, yeah. So we have these, we are using the short ensembles to do these tests, using a multivariate testing framework, and it's all packaged into the Eve framework that Joe developed. And we have done these power analyses to add to the knowledge of what the test can do and cannot do. And we have certain use cases that we have applied these test cases on. And we're expanding this capability to the MPAS-O model. And so we have generated these control and perturbed cases for the GMPAS NYF comp set, and we have done these case tests and Pucconi tests, and we have also done some power analyses, and we are moving forward with this. So the next steps and challenges for the MPAS-O case, we are going to, as I said, we are going to expand this trajectory of the control case of the GMPAS NYF, run it longer and use a more steady state from there. And then we want to do more power analyses using other parameter changes, and we want to evaluate the applicability of this test from low resolution that we're using here to high resolution. For example, at the 18 kilometer nominal resolution, there is no GM parameterization at all. So how can we do some tests there? And then we want to explore other multivariate tests for the ocean and use cases where there have been non-bit for bit changes in the past, and we want to use our test to see if we can catch those. And we want to integrate this to Eve, of course, so that this can be used by the larger community. And the next step is to extend these tests to individual software kernels. For example, the RTNGP, MD2 Club, MAM4, etc. And maybe we can use the single column modeling framework that has been developed now for E3SM, which can also have substantial spread in the model from the initial conditions or round-off errors. And there's a plot from Hack and Pedretti 20 years ago from the CESM single column model. And you can see that within about 100 hours, there's immense spread in the model here. And all this just comes from the perturbation, the initial condition. And then you want to investigate these tests on other model components, the land IC, etc. Right. So I just want to end with acknowledgements, and I'm going to take questions. Thank you.